Alright, so let's continue from the electrochemistry. We've done a redox reaction already, so I just want to talk about the voltaic cell and the electrolytic cell. When I'm talking about the voltaic cell, the redox reaction that occurs in the voltaic cell is a spontaneous reaction. So the reaction does not need any force or any battery or any chemical energy to apply to it before the reaction proceeds. For instance, taking this reaction, which is zinc solid and copper aqueous. In a redox reaction, they give zinc 2 plus and copper solid. So this is a typical example of this redox reaction that occurs in the voltaic cell. Now this voltaic cell is it mainly comprises two half cells, which we are having two electrodes. Now here is one electrode, this one is also another electrode. Depending on the position or depending on the direction of the flow of electrons will give you the anode and the cathode. The anode side is the position or the electrode where the oxidation reaction occurs, whilst the cathode side is the electrode where the reduction reaction occurs. Now let's try and talk more about it. So let's assume now one thing you're supposed to notice is that in the metal is dipped into a solution, and this solution contains the metal ions. So if you are having this side, if you are having this particular metal to be zinc and you are having this one to be sulfur, now the solution in which this one to be copper rather, now the solution in which you are finding the copper and this zinc will be an aqueous solution of that metal. So we may have our solution to be zinc sulfate. This will be our solution. Same way we will have our CuSO4 also. So this one is actually the solution. Now to make it very easy, let's try and indicate it with colors so that you understand vividly what I'm trying to say. Let's assume that the color of zinc metal is red. So the color of the zinc metal, the color of the zinc metal is red, while the color of copper is more like purple. Now the same thing applies here. So we have inserted these metals into the solution of what? So automatically this one is our zinc, which is red in color, and this one will be our copper. So having something like this, there is a redox reaction that is occurring, and this is the equation that I've illustrated here. So for this particular redox reaction, we are seeing that this zinc metal is undergoing oxidation reaction. This means it is, let me write the oxidation half. So our oxidation half, for better understanding, let's try and split our reaction into oxidation half and reduction half. So for our oxidation half, we are having zinc S giving you our zinc 2 plus, then plus 2 electrons. The same way we are having for our reduction half. For our reduction half, we are having our Cu2 plus 2 electrons, giving you the Cu metal. Here is the Cu solid. So all you have to notice is that if you are having a solid and now it is giving out electrons to produce Zn2 plus, which is a zinc 2 plus, automatically you are reducing the amount of the solid and you are increasing the amount of these ions, which is the ions that will be in the form of the zinc 2 plus. Now the same thing applies here, but this one is the opposite of it. Now we are having zinc 2 plus, and this zinc 2 plus is rather gaining electrons to produce what? Solid. And look at the direction of the reaction. So automatically you are going to produce more of the solid. That's what should come to your mind, so that it will help you determine the particular part of the metal that is reducing and the one that is increasing. So if you are having zinc metal, let's assume that the color of the solution, the color of the zinc sulfate is colorless. Now, if you are producing zinc 2 plus the 2 electrons, automatically you have connected it with wire. So this one's an electrode. So this is the direction of the electrons, which is the 2 moles of electrons. Now these electrons are actually moving through a wire to the other side of the electrode. So if we should replace this side with a bulb, or we should connect a bulb between these two wire, or these two connecting wire, it is going to glow because there is a flow of electrons. So automatically it will glow. So because there is a flow of electrons that is passing through the connecting wire. Now, if you are producing, you know that the color of the zinc metal is red, and now it is decreasing in mass. The moment you see something like this, it's actually decreasing in mass. So if it is decreasing in mass, the zinc 2 plus rather would be in the solution. So if the thing is colorless, you now see as time goes on, you are going to realize that what your solution in which the zinc metal is placed in will now be becoming more reddish. It will become more red. So the same thing applies here. Now, in this solution, we are having copper 2 plus. Remember that this one is actually a solution. In this solution, you're having copper 2 plus and SO4 2 minus. Now, we are having copper 2 plus. So the copper 2 plus here is also accepting 2 moles of electrons. Now, these 2 moles of electrons will add up to give you your copper solid. At the end of the day, you are going to realize that what your copper solid is giving you, the mass of the copper solid is increasing in size. Why? Because the zinc 2 plus is now gaining electrons to produce what's more of the zinc, the copper solid. So this is actually a copper solid, and now more of the masses will be increasing because there is a reduction reaction where it's accepting electrons to produce what the solid. So if you are having, due to the presence of this Cu2 plus, we may have the solution in which the copper metal is placed into, let's say, something like violet. Because of these ions, that's making the solution look violet. Now, if the concentration of these ions is being reduced by a reduction reaction, where it is accepting electrons to produce a copper solid, then automatically the color of this solution will reduce, or the color of this solution will fade out, because the ions that is making it look like, let's say, violet, is now reducing in concentration, or it is now reducing in the amount to give you your copper solid. So you are going to realize that the mass of your zinc here, so in terms of mass, you are going to find your zinc to be lower. The mass of the zinc will decrease, whilst the mass of the Cu solid will increase. But in terms of the ions, the zinc 2 plus will increase, whilst your copper 2 plus will actually decrease. So if this is the ion that is making the solution more, let's say, more violet, and now it is decreasing in concentration, automatically the color will fade out. Whilst if this one is the one that is making the solution, let's say, more reddish, it will make the color of the solution more red, because the concentration of the zinc 2 plus is also increasing. Now let's try and talk about the electric potential between the two electrodes. So looking at it from this side, the reason why we actually introduce a salt bridge is to actually maintain neutrality. Because if salt bridge is not involved in the galvanic cell, there will be a build-up of positive charges. For instance, you are having your zinc metal. This is the zinc metal, and this zinc metal is decreasing in size to produce more of the zinc 2 plus in the solution. So if a salt bridge is not introduced in the galvanic cell, more of this will be built up, more of the positive ions will be built up, whilst more of the negative ions, which is the SO4 2 minus, will also be built up, which will cause the reaction to actually cease. For that matter, we introduce this salt bridge to actually maintain a balance, or allow the reaction to proceed further and further. In the salt bridge, we may find an electrolyte. We have electrolytes like a strong electrolyte, which is the KCl, and this KCl, if you are having the salt bridge here, now we are saying that this salt bridge is made up of a KCl. So the KCl solution is, let me use this one to explain more. So you're having KCl in this salt bridge. Now for the positive charge, you have your negative ions from the KCl, you have your negative side of it, which is the chlorine, going into the positive side of the electrode. And this is to maintain it by providing electrons. And it's provide electrons, it actually minimizes the build up of these positive charges. The same thing applies to this side. The positive one, which is the K plus, will also go to this part of the electrode, and this one is going to minimize the buildup of these negative charges, so it will balance out and maintain neutrality. For that matter, we say that it will allow the reaction to proceed further. And now from the same diagram, let's try and talk about the cell notation. So when we are talking about the cell notation, it's actually a shorthand of writing cell, or it's actually a shorthand way of designing cells. For instance, if we are having this particular galvanic cell, we can write its cell notation. Because we are having zinc plus, and this zinc plus is undergoing the oxidation, we first write, and we are having our cell notation. Let me try and give you the, when we are having our cell notation, the first part of it should be our anode, where the oxidation occurs, followed by our bar, which is the salt bridge. So this side of it is the salt bridge. Then followed by our cathode. The cathode is the place where the oxidation occurs. So for this particular galvanic cell, if you are writing the electrochemical cell notation, then we can write it as our zinc solid. Always don't forget to bring the state. So zinc solid. And here, are we supposed to use comma or a bar? We are supposed to use bar because they are different phases altogether. We are having a zinc solid and what's giving you a zinc 2 plus, which is in aqueous. Now followed by our bar. This bar is actually representing the salt bridge. And we know the function of the salt bridge is actually to maintain the neutrality. Then followed by our aqueous again. So our aqueous Cu2 plus. Then we will bring a bar because we are separating it from a different phase. Then Cu solid. Now this is it. This is actually what you mean by our electrochemical cell notation. Now there's one hint I want you to give it to you. And you are writing the electrochemical cell notation and you are having something similar to this. Always make sure that you are starting with a solid and ending with a solid. The aqueous part of it will always be in the middle. I hope you understand this part of it. So let's try and write another reaction to where we are having our, let's try and write something here. We can also have CD, which is also solid, and now we represent it with a bar. Then we write our CD, which is also 2 plus, then aqueous. Then we bring our salt bridge. Then we write it moving on to the Ag plus, which is a silver, also in aqueous. Then our Ag solid. So this is also another example of the electrochemical cell notation. So if you are writing something like this, always make sure that you are starting with a solid and also ending with a solid for this particular type of. So if they give you a cell notation like this, you could actually see that this part of it is the anode side where the oxidation is occurring. So if you should replace this electrochemical cell notation into this particular diagram, you are going to realize that your CD will be here, then your CD2 plus will be in the solution, then this side will be your silver, and also our silver the silver, which is the silver ions, Ag plus. Now what you have to note is that if you look at something like this, automatically you'll be having the mass of the silver increasing, while the mass of the CD, which is the cadmium will be decreasing. So that's another way to also determine your electrochemical cell, how to interpret it. For instance, if you're having something like this, we are having our zinc solid moving to zinc 2 plus, automatically the mass is reducing, whilst our Cu2 plus is moving to Cus, or the copper solid, the mass is increasing. The same thing applies to this side. So this one is actually a typical example of the standard hydrogen electrode. And it's a standard hydrogen electrode because the gases that we are doing is hydrogen, as it is found in the name. But the reason why it is standard is everything is occurring at a standard condition, a temperature of 25 degrees Celsius. a concentration of 1 molar HCl and also a pressure of 1 atm. Now, what we have to notice is that we can't just allow this redox reaction to go by because we are starting with a gas. And starting with a gas, we have to include an inert material or inert electrode. For instance, the platinum or the carbon. Carbon can also be used in place of the platinum. The reason why we are using this is because this one, they don't react with any of the solution, and they also provide a surface for the reaction. They provide a surface for the reaction in a way that this inert material or this platinum will absorb, it will adsorb. Let me write it here so that it won't absorb, it will adsorb. So if it absorbs the hydrogen gas, it splits it into its atomic form. This one is, remember, this one is a hydrogen molecule or hydrogen gas, which is that appears in a diatomic form or more like a molecule. This time is going to absorb it and split it into its atomic form. Now, if it splits it into its atomic form, that's where it comes and see it as a bubble. So if you are writing the cell notation for this standard hydrogen electrode, first we have to include our platinum, which will start first, then followed by our hydrogen gas. So our hydrogen gas, which is the H2 gas, then separated by our hydrogen, which is the hydrogen plus or 2 of the hydrogen. This time around they are in aqueous solution. Then you will bring your salt bridge. So this one is actually, this is what is occurring at the anode side. So our anode, and what occurs at anode side is the oxidation. Now the same thing applies to the cathode side, but for the cathode side we are actually starting with our H plus. So our H plus will be in the solution, and it is what's reducing, it's undergoing a reduction to give you our hydrogen gas. So now we are having our H2 gas. Now we have to separate it with what? A platinum. So always make sure, if you are dealing with gas, you have to introduce an inert material, which is either, so for this side of it, this is a salt bridge, then this side will be our cathode. So now let's try and determine the electrode potential at each of the various electrodes. Now if I do talk about the standard hydrogen electrode, which is a She, and we always know that what the electrode potential for the standard hydrogen electrode is always 0 volts. So the moment we connect this standard hydrogen electrode with anything at all, any value that we record will be assigned to the electrode potential of that particular electrode. For instance, this one is a standard hydrogen electrode, and this one is also a standard electrode. Standard in a way that it's having a concentration of 1 molar and it is occurring at standard conditions. We have connected it with this standard hydrogen electrode. For that matter, if we should set everything into place where everything will be in the solution, we are going to have our salt bridge. We are going to have our salt bridge and everything. Now, if the reaction should proceed, we are going to get a flow of electrons. This one is actually a zinc, so we are going to get a flow of electrons from this side. Then this will be the direction of the electrons. So automatically we are going to detect some change in voltage here. So the change in voltage that from the slide, the change in voltage was E0 to be equal to 0.76 volts. So this is it. Now we know that this side is the anode and this side will be the cathode. Okay, so now to proceed with, if you want, even looking at this particular electrochemical cell, if you want to determine the cell notation, it will be very easy. The cell notation is actually your zinc solid. Your zinc solid. Then you separate it by a bar because you are moving from one phase to another. Then your zinc 2 plus. But because you are dealing with standard conditions, you bring your 1 molar, indicates that this one is actually aqueous. Then you bring your 2 bar. This is the salt bridge part of it. Then automatically, because you are introducing hydrogen into it, I've already explained to you that this inert material will absorb this hydrogen gas, split it into H plus. So now we are having our H plus aqueous, which is also what, 1 molar. Then moving to our hydrogen. Now you see, before we are introducing the hydrogen into it, we said that everything is what, under standard conditions. So automatically the pressure here to also what, 1 atm. So under standard conditions, now we are having our hydrogen gas. Now this hydrogen gas comes with what? 1 atm. Now before we introduce our platinum, which is the inert material, so our platinum is here, platinum solid. So this is how we are going to go by your cell notation. Now if you want to determine the electrode potential for especially zinc, if you want to determine it, there is a formula that states that our electrochemical cell E0 of the cell is given by the one at the cathode. So E0 of the cathode followed by, so minus the E0 of the anode. So if you know this formula, automatically what is happening at the cathode side? At the cathode side, we are having our H plus, then our H2, and at the anode side, we are having our zinc 2 plus, then our zinc solid. So this is how you are going to go by it. So automatically, now how do we identify our E0 of, let's say, the zinc? You see the E0 that we are having here, you see the formula is what? E0 of the cell. Now where is the E0 of the cell? The E0 of the cell is the value that has been recorded from the voltmeter. Assuming this one is a voltmeter, if already recorded the voltage across this, so the PD across it is what's given by, let's say, 0.76. Now where we are going to see our E0 of the cell, we replace it with 0.76 voltage, because that is the E0 of the cell. So this E0 of the cell will be equal to, now the E0 at the hydrogen side, we always know that it is 0. Sorry, and that is the electrode potential for the one at the hydrogen side. So minus your E0 of, let's say, your zinc 2 plus, then zinc N. So now all we have to do, we are having 0 here, so we have to just make this one the subject. So our E0 of the zinc 2 plus slash Zn is equal to negative 0.76 voltage. So this is actually your value for the E0 of the zinc. So like we all know, the moment you are connecting your standard hydrogen electrode with any of the electrode at all, it means that you want to determine the standard electrode potential for that particular electrode that is connected to the hydrogen, because always know that our hydrogen, the standard electrode potential for the hydrogen is always 0. So